Alrighty, so we're just going to kind of continue doing what we were doing before, where we assess if it is Markovnikov or anti-Markovnikov. Uh, if it has a chance of carbocation rearrangement, we'll look at the reagents and then we'll predict the major product for each of these. Okay, so let's first look at the reagents. So we have a catalytic acid, which will turn into H3O. It's okay. And I'm recording at home, so you might hear my kids in the background. Um, okay, so we know our catalytic acid is going to be H3O. We're not doing the mechanism for this, so that's not really super important. What is important, however, is that we notice that this is not water. This is an alcohol, it's ethanol. Uh, if we come back here and we look at this right here, we see that it's got H3O and H2O. But that H2O can also be an alcohol. And we did that in problem 1, I think. Yes, right here, where we had the same reaction, but instead of water, we have an alcohol. So what you have to notice is that when you have an alcohol instead of water, you're going to be making an ether. So with water, you're making an alcohol. With an alcohol in the reagent, you're making an ether. Okay, so this is a Markovnikov reaction. So our ether is going to be added to our more substituted. So we want to go ahead and assess our alkene carbons as our more and our less substituted. And then we just have to predict the major product. We don't have to do the mechanism. But if it's helpful to you to be able to see where things go, I recommend doing the mechanism just as a practice. Okay. So the other thing that we have to do is predict, or not predict, but assess if there's going to be a carbocation rearrangement, right? So this is Markovnikov, so our hydrogen added to our less substituted alkene carbon, and our carbocation is on our more substituted alkene carbon. And now we need to assess the two carbons that carbocation is attached to and whether or not we can do any shifting to make it more stable. So we want this to be on the most substituted carbon it can be on. So we know it's not going to go here because that's less substituted. Can it go here? So we have to look at, are there any hydrogens attached to this carbon or any methyl groups that we can move around? So there is a hydrogen attached. Let's do it in a different color. There is a hydrogen attached to this carbon. So we can do a hydride shift and move our carbocation over. And we get this product right here. So with Markovnikovs, unless it's oxymercuration, demercuration, and anti-Markovnikovs, unless it's hydroboration, oxidation, you need to assess for carbocation rearrangement. All right, and so now we've rearranged it. We don't have to draw the mechanism, so we just add on our ether to that carbocation, and remember that it's an ether because instead of water in the reagents, we have an alcohol. O, and then this is our ethyl group. And there is another way to rearrange that carbocation where you open up the ring, but again, I really do not understand that. So out of my depth. Okay, so our next reaction, let's assess the reagents. We have the oxymercuration, demercuration, and then we also have something that's a little bit different here. Let's highlight it in a different color. So if we look at our addition reaction summary page, right here, it again has water, just like up here, but over here we have, oops, an alcohol. well, let's do it in blue. So we have an alcohol, not water, and it's going to do the same thing. It's going to make it an ether instead of an alcohol. And then another important factor for our oxymercuration demercuration is that there is no carbocation rearrangement. So we're just going to assess our more substituted, least substituted carbons. And we're going to add our ether to our more substituted carbon because it is a Markovnikov reaction. Markovnikov, and I'll put no rearrangement. No rearrangement. Because it's oxymercuration demercuration. Okay, and then, yep, we want to make sure that we know that this is alcohol, so we're going to be making an ether. We're adding an ether instead of an alcohol. So we're just going to add that on to our more substituted alkene carbon, which is this guy right here. And then there is our ether. All right, one more, and this is the same, these are the same reagents. I don't know if it's in the notes that shows how to do these reactions where it's going to be an intermolecular attack or intramolecular attack. So what happens is, if you noticed here, and I don't know if he's talked to you guys about this, but like up here we have alcohol in our reagents, and up here we have water. So we know we're adding an alcohol to that one. We're making an ether out of this one. This one doesn't have anything attached to it. However, it is already a part of the molecule. It's this alcohol. So it's as if we have an alcohol here. And it's going to do an intramolecular attack. So what happens is it's Markovnikov. So we know it's going to attack the more substituted. The alcohol, the ether, is going to attack the more substituted. So let's put ROH attacks more substituted alkene carbon. Didn't even finish that word. So let's assess our carbons. So that's our more substituted. And here's our less substituted. So we know it's going to attack our more substituted. It's going to attack this carbon right here. Well, what does that look like? And it's actually the nucleophile, the alcohol, is right here. It's in the molecule. That's why it's an intramolecular attack. So the way that you want to draw these is you want to, first of all, label all of the molecules that are going to be a part of the reaction. So we know that the alcohol, or the oxygen in the alcohol, is the thing that's doing the attacking. So we want to number that. It's important. Usually we just number our carbons, but we want to number the alcohol because it's going to be taking these electrons and attaching them to this carbon, the more substituted carbon right there. Okay, so we're going to label that 1, this carbon 2, 3, 4, 5, and the important carbon here is 6. We do have a 7, but it's going to kind of be outside of the ring, and that's kind of something important for you to recognize too, and you'll see what I mean when we draw it. But this right here is going to be outside of the ring. So let's, I'm going to redraw our molecule. Make sure I did that right. 1, 2, 3, 4, 5, 6. Okay. Here's our alkene. Oops. Okay. So we know that it's going to attack right here. And it's going to be these electrons that do the attacking. So before the oxygen attacks, these alkene carbons are bonding with this mercury right here. And we don't need to know the mechanism for that, but you can recognize that we're not using this to attack the alkene carbons, right? Um, when we do this, let's go back up to this guy right here. So remember that the catalytic acid was the one that attacked the alkene electrons, right? And that's the same thing with our oxymercuration, demercuration. It's going to be the mercury that attacks the alkene carbons, and then the alcohol comes in as a nucleophilic attack. So it's this essentially that's going to attack these to open up the double bond. And then the alcohol is going to attack. So let's draw it as if the HGOAC has already attacked. Let's draw what that would look like. Six. Okay. And then it forms a sort of like the epoxide. So that's what it would look like, but we don't really even need to know that. All we need to know is that now this is the carbon that's going to be attacked by our alcohol. And so what I like to do, because I find these a little bit difficult, is 2, 3, 4, 5, 6, 7. Make sure that they're numbered. And I look at the carbons that are going to be involved in the ring and kind of count those. So I I draw and actually let's draw it. I draw a box around the stuff that's going to be in the circle, and then anything outside of the circle will be outside of the circle. So I know I have a 6-membered ring, but it's going to have the oxygen as part of that ring, which is why I numbered it as 1. It's not just going to be all carbons. It's not going to be a cyclohexane like this. It's going to have an oxygen right here. See that? So let's number this. Oops, I forgot to draw the H. So let's draw the H. Okay, so we have our 1, which was on our oxygen, 2, 3, 4, 5, 6. And then remember we have this guy right here. So we have to draw him in. It's just a little methyl group, and he comes off of carbon 6, boop, just like this. Why did I draw an arrow? All right, so if you were to do your formal charge, you would see that that oxygen now has a plus on him. We know that he doesn't want a plus on him. So it's just as before when our alcohol first acted as a nucleophile, then it acted as a Bronsted base, the same thing happens here, except that it's the HGOAC that does the deprotonating. So again, you don't have to know the mechanism, but you just have to recognize that the hydrogen, oops, we don't need this, the hydrogen gets plucked off, and you get left with 1, 2, 3, 4, 5, 6. An ether, it looks like that. So that's how you do an intramolecular attack. And again, if you are wanting to just go over it real quick again, there was nothing here. It was blank. And so if you look over here, we can see that the nucleophile is actually a part of the molecule. We assessed where the more substituted, less substituted carbons were. We talked about how the alkene carbon opens up and forms this triangular bond, cyclic bond with the mercury. And then stuff happens and the mercury leaves, and we are able to attack from this 1 oxygen to this 6 carbon, and we drew a cyclic molecule. and we added on our methyl group that was kind of poking out at the end. And we don't have to know the mechanism, but we do need to recognize that there was an H attached to this O and it gets deprotonated, and we are left with an ether.